Good day, everyone. I am Valdez, a graduate student from University in Tokyo, Japan. Thank you for your participation in this virtual international conference in coastal engineering. My presentation for today is Analysis of a School Building Against Typhoon Haiyan Storm Surge Forces. As mentioned, I am currently studying at University under the supervision of Professor Tomoya Shibayama. I am from the Philippines, and my research interest is in coastal disaster prevention in my home country. For my graduate studies, I have focused on numerical simulations of Haiyan and other typhoons. Since the Philippines are frequented by typhoons, I decided to study storm surges and how to minimize damages to structures. Perhaps one of the most storm known storm surges in recent history is from Typhoon Haiyan in 2013. It brought storm surges of up to 7 meters at Tacloban City, a highly urbanized area in the central part of the Philippines. Haiyan was one of the costliest typhoons in terms of damage to structures. Typhoon events usually cause massive damage to structures. Typhoons bring strong winds and landfall. If certain conditions are met, storm surges could happen at the coastal area. After a typhoon event, damages to structures should be investigated for rebuilding and to prepare for future events. In the view of research, the focus of damage assessment is typically on the hazards like wind speeds and flood depths. However, for engineering practice, it is important to consider the forces that the structure may experience due to a typhoon event. Combining these two views, research and engineering practice may significantly improve assessment damage to structures. In the Philippines, public school buildings are usually used as evacuation centers during a disaster. 2 years after Haiyan, the National Structural Code of the Philippines was updated. This code was used to design new public school buildings. Since many public school buildings were destroyed by Typhoon Haiyan, there is a need to check if the new design can survive another similar storm surge event. Thus, the objectives of this study are to accurately simulate the 2013 Typhoon Haiyan and storm surge at San Pedro Bay using numerical models, and to investigate the strength of the beams and columns of a standard two-story public school building at Tacloban, subjected to the wind flood forces from the simulations. The location of San Jose National High School in Tacloban was selected for this study. The integrated numerical model used has three components: weather, surge, and structure. The WRF was used to simulate typhoons. Then, FVCOM was used to generate storm surges and inundation. Finally, STAAD.Pro was used for structural analysis. The Weather Research and Forecasting Model, or WRF, is a numerical weather prediction model. Input geographical and atmospheric data are first prepared using a series of programs. There's an option to improve the initial boundary conditions using tropical cyclone bogus-ing, or TC bogus-ing, a data assimilation procedure wherein the existing tropical cyclone data are replaced with a bogus tropical cyclone using a Rankine vortex-based wind profile centered at the desired location. Then the typhoon is simulated using different weather equations and physics operands. The typhoon track, wind data, and pressure data can then be extracted from the simulation. The Finite Volume Community Ocean Model, or FVCOM, is a storm surge numerical model that utilizes the flexibility of finite element method and computational efficiency of finite difference method. Using the wind and pressure data as input, the change in water level over a mesh system is calculated using different flow equations. The output are time series storm surge data, inundation data, and inland wind data. Finally, STAAD.Pro is a three-dimensional structural engineering software that is capable of performing static and dynamic analysis. The structure can be easily modeled in STAAD.Pro and analyzed under the computed driving forces from FVCOM. The resulting beam and column forces can be obtained using static linear analysis and compared to the design strength of the structure. For the WRF simulation, a parent and nest domain setup covering the track of Typhoon Haiyan from its early formation in the Pacific Ocean until its departure from the Philippines was used. The atmospheric files used for this study is the 6-hourly global forecast system 0.5 degree by 0.5 degree resolution data. Since it is difficult to simulate strong typhoons such as Haiyan, the TC-Boson scheme was utilized. For the WRF results, the comparison of the simulated typhoon tracks with the observation data over domains 1 and 2 are presented here. It can be seen that the TC-Boson scheme was able to significantly improve typhoon track, which is very important for SUMSTER simulation. The simulated minimum sea level pressure and maximum wind speed of the typhoon also significantly improved when TC-Boson scheme was used. Thus, the Typhoon Haiyan simulation was successful in the WRF model. For the FVCOM simulation, a propagation mesh was used to generate the storm surge at San Pedro Bay. Then, a nested inundation mesh at Leyte was then used to generate the flooding in the area. The simulated change in water level during the passage of Haiyan at San Pedro Bay are shown here. The water surface in the bay first decreased before increasing up to 7 meters as Haiyan made landfall at Leyte. The FVCOM results were validated using field survey data from these two research groups. The storm surge simulation results at the Tacloban area agreed well with the field measurements. The following are the time series inland wind and flood data at the location of San Jose National High School in the inundation mesh. In this scenario, the peak inundation depth of 3.15 meters almost reached the second floor of the building, which has an elevation of 3.45 meters. These results were used to compute for the wind and flood forces to be applied on the public school building. 4 general loading types were applied in the model structure in STAAD.Pro during the simulated storm surge event: dead load, the live load, the wind load, and the flood load. The flood loads were composed of the hydrostatic, hydrodynamic, and breaking wave loads. For simplification, the load combinations were applied to both the global positive x and positive z axis to indicate the direction of wind and surge forcing. The wind loads were applied to the exposed members of windward, leeward, and sidewall sectors of the structure, while the flood loads were applied on the vertical members based on the calculated inundation depth and flow speed from FVCOM. A total of 300 beams and columns were analyzed. The capacity of each member was compared to the internal forces under two scenarios: strong wind only and strong wind with storm surge. Critical members were then determined. Here is a portion of the structural analysis results, showing the maximum axial forces experienced by the corner columns. No significant change between two scenarios were observed since typhoon forces acted laterally to the structure. For the maximum shear forces and bending moments, there were significant increases observed at the ground floor columns when surge was considered, since the flood loads acted on these members. For the whole analysis, all designed beams and columns had sufficient strength to resist failure against the Typhoon Haiyan storm surge forces. Based on the results, the driving forces due to the storm surge increased the shear and bending moments at the ground floor columns. Again, this was expected since the flood loads acted on the vertical members. But overall, the beams and columns of the public school building were strong enough to resist the driving forces of Typhoon Haiyan, probably due to the high seismic design provisions of the structural code. However, caution is caution on interpreting these results are emphasized, since the reload was not included and only the beams and columns of the structure were analyzed. The overall performance of the structure may vary when other parts such as the behavior of the foundation and roof truss are considered. But in a simplified view, the beams and columns can give a general idea on its strength since it forms on the structural frame of the building. Therefore, the results should not be interpreted as a guarantee of survivability of the design school building against another Typhoon Haiyan storm surge event. The highlight is the methodology to analyze any structure at any location against a storm surge event, given the versatility of the numerical models. In conclusion, the WRF FVCOM STAAD.Pro integrated model was able to accurately simulate the Typhoon Haiyan storm surge event at San Pedro Bay and Tacloban, and determine the driving forces needed to investigate the strength of the beams and columns. It was observed that the ground floor columns were critical members in the case study. Although all members had higher strength capacities when they applied wind and flood loads, there is still a need to check other loads and response of other structural members. This is the end of my presentation. Thank you for listening.